Earlier, we have been estimating the population mean using a sample size. But now, we are going to estimate the sample size given a population standard deviation. And when we do that, we incorporate the error of estimation, which is x bar minus mean. Error of estimation gives you a cushion, an allowance in the estimations that you're going to compute for. And so when we estimate the sample size, the formula that we will be using is n equal to z-score multiplied by the population standard deviation over e raised to 2 or squared. So E here is the error of estimation, which is x bar minus mean. So let's put this into practice with this example. Suppose a researcher wants to estimate the average monthly expenditure on bread by a family in Chicago. She wants to be 90% of her results. How much error is she willing to tolerate in results? Suppose she wants to estimate to be within $1 of the actual figure and standard deviation of monthly bread purchases of $4. The value of z for 90% level of confidence is 1.645. What is a sample size estimation for this problem? We need to write down all of the given or all of the values that are needed to compute for the n. And so we have here the error of estimation, which is 1. It was mentioned earlier that she wants the estimate to be within $1. And for the standard deviation, we have $4. And as for the z-score, it's mentioned already in example, it's 1.645. And so we only need these 3 values to compute for the sample size. And so we have 1.645 multiplied by 4 over 1, and all of these are squared. It gives you the answer of 43.2964, but since we're talking about sample size, it has to be whole, especially for this one, that bread. When you are selling bread, you don't sell half bread or 0.2964 of a bread for the same price. So for sample sizes, you truncate the decimal places. You do not round it up, you do not round it down. You truncate it, meaning you remove all the decimal places. So instead of 43.964, you now have 43 as the sample size. So just like before, we can also do statistical inferences in estimating the sample size using the proportion. The formula that we will be using here is n is equal to p hat q hat multiplied by z over the error of estimation squared. So let's take this example. The Hewitt Associates conducted a national survey to determine the extent to which employers are promoting health and fitness among their employees. Does their company offer on-site exercise classes? Suppose it was estimated before the study that no more than 40% of the companies would answer yes. How large a sample would Hewitt Associates have to take in estimating the population proportion to ensure a 98% confidence in the results and to be within 0.03 of the true population proportion? So let's write down all of the given. So p hat is equal to 0.40 and q hat is 1 minus p hat. And so it is 1 minus 0.40, which gives you the answer of 0.60. The confidence interval here is 98%. When converted to z-score, it gives you 2.33. And the error of estimation is 0.03 because it was mentioned in the example that the company wants the result to be within 0.03 of the true population proportion. So now we have 0.4 times 0.60 times 2.33 over 0.03 squared. We have 0.24 times 6,032.11, and which ultimately gives us the answer of 1,447.7067. Since we're estimating the sample size, specifically how large the sample size would be or how many people would answer yes, then we will have to truncate the decimal places, meaning we don't include the decimal points anymore. Instead of 1447.7067, the answer or the sample size that we're looking for is 1447.